Welcome back, students. So we are going to continue with the chapter that is hydrogen. And in the previous class, we have discussed about the hydrogen's occurrence, what is the nature of the hydrogen, and how the isotopes of hydrogens are different from each other, and what are their physical and chemical properties. Okay. Now let's move further and talk about the hydrides. Okay, the hydrides of hydrogen. So what are the hydrides? So generally the hydrogen can combine with almost of all of the elements. Okay, that is metals and non-metals. It can easily combine and it can form hydrides. But it cannot combine with the noble atoms. Okay, it cannot combine with the noble gases. That is helium, argon, neon, and all these elements. It does not generally compound. Okay, and what are hydrides? So how we can define the hydrides? So hydrides can be defined as the the binary compound of the binary compounds of hydrogen with other elements. Okay, the binary compounds of hydrogen with the other elements, they are termed as what? They are termed as hydrides, are called hydrides. They are termed as what? They are termed as hydrides. Generally, the general formula for hydride, general formula for the hydrides, the general formula for the hydrides, it will be EHX. Okay, it will be EHX, where E will be the element that can be either metals or non-metals, and HX is the number of the hydrogen atom attached to that metal or non-metal. Okay, or you can also form, it can also be termed as EMHN. Okay, EMHN. Now, how they are formed by? Okay, how they are formed. So number one, all main group elements can form hydride. Okay, all main group elements can form hydride except the noble gases, except the noble gases and indium and thallium. Okay, indium and thallium. Two more exceptions are there, that is indium and thallium. They also does not produce the hydrides. Indium and thallium. They also does not produce the hydrides. All lanthanides, all lanthanides and actinides, all lanthanoids and actinoids, they will also form hydrides. All the transition elements, all transition elements, that is scandium, yttrium, lanthanium, actinium, technetium, zirconium, etc. And to very lesser extent means the chances of hydride formation will be low here with vanadium, niobium, talcium, calcium, chromium. Okay, this is chromium, copper, and zinc. Okay, they can also form hydrides, but the chances of forming hydrides with the below elements, it is low. Among the transition elements, sorry, not elements, the metals. Okay, they are generally metals, so we are representing it as metals. Among the transition metals, palladium hydride, palladium hydride has been extensively studied. Okay, it has been extensively studied out there. Now, on the basis of their physical and chemical properties and on the types of bond, the hydrides can be classified. Okay, classification of hydride. And the classification of the hydride is on the basis of their chemical and physical properties and also their type of bonding. So, there are generally three types of hydrides. The number one hydride is the ionic or salt-like or saline hydrides. Saline hydrides. The number two is the covalent or molecular hydrides. And the number three is the metallic or interstitial hydrides. Metallic or the interstitial hydrides. So these are the three types of hydrides which are generally classified on the basis of their chemical and physical properties and also on the type of bond which they are forming. So first let's discuss about the ionic hydrides. The ionic hydrides. So what are the ionic hydrides? When metals with low electronegativity okay, when metals with low electronegativity combines with hydrogen combines with hydrogen and they are they are electropositive, then hydrogen. Okay, they form what? They form the ionic hydrides or saline hydrides. So here generally the S block elements, okay, that is group 1 elements, the group 2 elements, okay, they will form the saline elements. Also some other, that is lanthanum, okay, lanthanum can also form the saline hydrides. So how they are formed? These are formed, these are formed by transfer of electron, by transfer of electron from metal to hydrogen atom and contain hydrogen as H minus ion. Okay, so here we can take the examples Ionic hydrides are generally formed with the direct combination of metals with hydrogen at very high temperatures. Okay, so here we can take the example for lithium, which will readily combine with hydrogen to form lithium hydride. Okay, potassium also combines with hydrogen at temperature of 633 Kelvin to produce potassium hydride. Calcium will also combine with the hydrogen at 1073 Kelvin to produce calcium hydride. Strontium will also combine with the hydrogen at 1123 Kelvin to produce strontium hydride. So the general characteristics for the hydrides, okay, with the ionic hydride, general characteristic for ionic hydrides. General characteristics for the ionic hydrides. So first here is the ionic hydrides are generally white or light gray. Ionic hydrides are generally white or they will be light gray. They are non-volatile and non-conducting crystalline, non-conducting crystalline solids. They behave as salt. They behave as salt and are also referred as salt-like hydrides. Okay, salt-like hydrides. However, we will see that beryllium hydride and magnesium hydride, they are not ionic, are covalent, and also in the covalent they are polymeric. Okay, they are having polymeric structures. So both of these, that is beryllium hydride and magnesium hydride, they cannot be considered as a ionic hydride. They will be having covalent nature. They have high melting and boiling point. Melting and boiling point. The binary hydrides, the binary hydrides of alkali metals, here examples can be taken for LiH, NaH, KH, CSH, and etc. have rock salt like structure. Okay, they will be having the structure which is similar to that of a rock salt. They conduct electricity in fused state. They conduct electricity in fused state. The negative charge on hydride negative charge on hydride is proved by electrolysis. Okay, it is proved by the electrolysis method. Electrolysis of molten lithium hydride at 973 Kelvin. Here, when electrolysis will be done, let us take an example for lithium hydride. Okay, for lithium hydride, if I am carrying out the electrolysis, then at 973 Kelvin, the lithium and hydrogen will decompose into lithium ion and hydride ion. And at cathode, for this electrolysis, lithium will accept one electron to form lithium that is deposited at cathode, and at anode the hydride will release one electron to form hydrogen, and two of the hydrogen atoms will combine with each other to release out as a hydrogen gas. So this shows the existence of that H minus ions. Okay, so the existence of H minus ion is been proved here. And here we will see that 2H minus, it melts to form H2 gas, and releasing of two electrons will take place. Okay, so hence by using the electrolysis method we have proved that the metal hydrides or the ionic hydrides, they are containing hydride ion, which is negatively charged hydrogen. Their densities, the next property, the next characteristic for the ionic hydride is that their densities are very higher. Okay, they are higher in density than those of metals. Their density will be more higher as comparison to that of the metals. Lithium hydride, calcium hydride, and strontium hydride, these are one of the examples for the most stable hydrides. They are the most stable hydrides. Other hydrides undergo thermal decomposition. Other hydrides will go thermal decomposition above the temperature of 775 Kelvin. Okay, they will undergo the decomposition after the 775 temperature. Here the thermal stability can be denoted for the first group by the relation that lithium hydride more stable, sodium hydride less stable than lithium hydride, potassium hydride less stable than the sodium hydride, rubidium hydride less stable than the potassium hydride, and the least stable is the cesium hydride. Okay, for the group 2, calcium hydride is more stable, strontium hydride is the intermediately stable, and barium hydride is least stable. Here magnesium and beryllium hydride is not included because they both are having covalent nature. They are not ionic in nature, so therefore they are not included here. So here we can see that the lithium hydride, the calcium hydride, and strontium hydride, they are having more stability as comparison to that of the other hydrides which are formed by group 1 elements or the group 2 elements. And this is cesium hydride. Okay, CSH. Next property, next characteristics which we can see here is that ionic hydrides, ionic hydrides are oxidized by air to form metal oxide and water. Okay, the ionic hydrides, they will oxidize with air to form metal hydride and water there. So if I am taking 2EH, they will oxidize with the oxygen present in the air to form metal oxides and water. RBH, that is rubidium hydride and cesium hydride, simultaneously burns. Okay, they simultaneously burns at room temperature. It will simultaneously burn at room temperature, means they are very very reactive or very very volatile substances. While lithium, okay, lithium hydride is unreactive. Lithium hydride is unreactive to moderate temperature also. Moderate temperatures also. Next, the next property, the next characteristic here is that they are hydrolyzed by water with formation of hydroxide, with formation of hydroxide and liberation of hydrogen gas. Liberation of hydrogen gas. So lithium hydride will get hydrolyzed to form lithium hydroxide, water, sodium hydride will hydrolyze with water to form sodium hydroxide and hydrogen. So this shows that their aqueous solutions are basic in nature. Okay, they are basic in nature. So these were the ionic hydrides. Okay, so we have discussed about the ionic hydrides here and their different characteristics. Now let's see the use for the ionic hydrides. What are the uses of the ionic hydrides? So first, the ionic hydrides are generally used as good reducing agent. They are good reducing agents. Okay, they are very good reducing agent, and for this we can take an example for lithium hydride combined with aluminium chloride. Okay, aluminium chloride, Al2Cl6. It will form lithium aluminium hydride with lithium chloride, and this lithium aluminium hydride is one of the good reducing agent. Similarly, when lithium hydride is reacted with diborane, then it will form, in the presence of dry ether, in the presence of dry ether, it will form lithium borohydride, which is also a very good reducing agent. Similarly, when sodium hydride is reacted with diborane in the presence of dry ether, it will produce sodium borohydride, which is also a very good reducing agent. So hence these compounds, which is lithium aluminium hydride, sodium borohydride, okay, and lithium borohydride, they will be used as reducing agent and one of the good reducing agents, okay. Also they are used as solid fuels, okay. They are generally used as what? They are generally used as solid fuels also. In some places we will see that they will be used as solid fuels. So this was for the ionic compounds, okay, ionic hydrides. We have studied about the different characteristics and also the uses of the ionic hydrides which been seen out here. So this is for the ionic hydrides. Until here only we are going to conclude in this class. In the next class we are going to see the covalent or the molecular hydrides. Okay. So thank you for this class. We will continue in the next class. Thank you.